Welcome everybody to Conceptual Astrophysics, a series of videos in which we set up and solve introductory astronomy problems. I'm your host, Dr. Christopher Sorolla. Today we're taking a look at Kepler's first law, and specifically properties of ellipses as they pertain to objects that orbit the sun. So let's imagine the following, and please forgive my rough sketch here. Let's imagine we have an asteroid that is orbiting the sun. Its semi-major axis is a distance of 5 astronomical units, and by looking at the orbit, astronomers note that the distance from the center of the orbit, notice that the center of the orbit is actually empty space, to the position of the sun is 3 astronomical units. So our questions are these: determine the eccentricity of the orbit, the perihelion of the orbit, and the aphelion of the orbit. So let's do a little bit of sketching so we can maybe figure out a little bit what's going on. So I've already got the oval more or less drawn, and the position of the sun is noted. Now over here I've labeled this position F. That is the other focus of the ellipse, but as you probably have already learned in astronomy classes, there's nothing there. That part of the ellipse is simply empty space. So let's go ahead and sketch a major axis across the ellipse. Now by definition, the major axis, of course, goes through the center, and then both foci, or focus positions, of an ellipse. So that's our major axis. And more carefully, this distance from here to here, from one edge to the center, is the semi-major axis, or little letter A. So if we go ahead and put together our table of known quantities, we can write down the number for little letter A, and go ahead and sketch it on the picture so it's understood what that is. All right, next question. The distance from the center of the orbit to the sun is 3 astronomical units. Now I've got the sun labeled, and let's also sketch that out. So this distance here to here. Now in astronomy and in mathematics, the symbol for this distance is called little letter c. Now there isn't a short name for this, unfortunately, perhaps, but that's what it is. The distance from the center to one of the focus points would be little letter c. By the way, I could have also drawn it from here to this other empty focus, but of course it makes more sense to draw it to the sun. But in any case, little letter c is 3 astronomical units, like that. Okay, so those are the known items. What is unknown about this object's elliptical orbit? Well, the eccentricity, which is the little letter e, perihelion, which is commonly abbreviated PE, and aphelion, which is abbreviated AP, like that. Now, just to mention a quick thing about this, in English, the 2 letters that go together, PH here, is often a F sound. So there's a tendency to think that you might pronounce it aphelion, but that's not correct. Because app is a separate prefix to this word. So ap and then helion, as in helios, as in the sun, is what you're talking about. So ap is a prefix that means furthest, helion, sun, literally furthest from the sun. It's a little bit easier with para. Para is closest, and again helion, so closest to the sun. So the perihelion position will be over here, if you will. So from the sun to when the asteroid is at this spot in its orbit will be PE, like that. And way over here, when the asteroid is at that spot, that'll be our aphelion position. And we can sketch it in something like this. So you see I've got these lined up so they actually do go out to that furthest spot like that. Okay. So a couple things to note before we even get started. One is the semi-major axis, of course, is halfway across. The major axis is all the way across. The perihelion plus the aphelion is also the same as the whole major axis, or twice the semi-major axis, if you will. So that's one thing that comes in already. But here's the thing that's going to help us solve the problem a little bit more quickly, and that's the definition of eccentricity. So eccentricity is the amount of stretched outness, if you will, of an ellipse. And the smaller little letter c is, the less stretched out it is, the more like a perfect circle it looks. The more stretched out c is, the more stretched out the whole ellipse is, and the really stretched out then the whole ellipse is. So eccentricity, by definition, is c divided by a, like that. By the way, real quick aside, if you're wondering what happened to the little letter b, the little letter b is the semi-minor axis, and we go from the center to the edge here. We don't need that for this problem. We could use it if we want to solve other aspects of the orbit of the asteroid, but we're not worried about that today. So, little c over little a, 3au then, divided by 5au, and I think that's easy to see. That'd be 0.6. So, a couple things about eccentricity. One, there's no units on eccentricity. Astronomical units cancels astronomical units. Or if you're sketching this picture to scale in a lab, let's suppose that from here to here was 3 centimeters, and from here to here is 5 centimeters. Again, 3 centimeters divided by 5 centimeters, the centimeters cancel. So eccentricity is a unitless quantity. That doesn't mean it doesn't have any meaning. It just means the units are missing. It doesn't have any. Okay. Second thing is, what about perihelion and aphelion? Well, perihelion is equal to the semi-major axis multiplied by 1 minus the eccentricity, like that. And so let's go ahead and calculate that. So semi-major axis is 5au. Now that we have eccentricity, 1 minus 0.6. Of course, 1 minus 0.6 is 0.4. So 5au multiplied by 0.4, or 40%. 40% of 5 is 2. So the perihelion distance is 2au, like that. Aphelion is a similar sort of idea, except instead of a minus sign, it's a plus sign. So A1 plus that, all right? So 5au, now it's 1 plus 0.6, or 5au multiplied by 1.6, like that. And 1.6 multiplied by 5 is 8. So, double check my math, but 1.6 times 5 will be 8. 8au. That's something you should always do, by the way, whether it's your professor in class doing a problem, or you're watching a video, whether it's here or somewhere else, and they perform a calculation. Probably should always check the results. Now, granted, in a video, the whole point of a video is that they're showing you the correct answers, right? They're showing you how to do this properly, but it's still a really good idea. Not only just to double check them, but also to make sure it's correct for your own sake. All right. Last thing, I wanted to double check here. By the way, these are the answers, but I said before, the perihelion plus the aphelion must be twice that of the semi-major axis. So, perihelion plus aphelion is 2 plus 8 au, which of course equals 10. 2 times the semi-major axis is 2 multiplied by 5 au, and lo and behold is also 10. So our answers are confirmed, if you will. We have double checked our answers to make sure that they do work the way they're supposed to work. Okay. So why would you care about the closest or furthest position of an asteroid or a planet or anything else from the sun? Well, one thing would be that the amount of sunlight you get if you are closer is obviously brighter, right? By how much? Is it really distinct, or is it very different? And if you take a look at perihelion versus aphelion for our sample asteroid here, 2au is 4 times closer than the aphelion. The temperature, or the sunlight you're going to get, say, at the perihelion, is the square of that ratio. So 4 squared is 16. The sun will look 16 times brighter here at perihelion than it would at aphelion. There's a significant difference in temperature and the heat and the light that you receive from the sun for this particular asteroid at the extremes of its orbit. Now, that is for this imaginary asteroid, right? That's not necessarily for actual astronomy objects, but there are some comets and asteroids that do have eccentricities this large. It's not unheard of. It's not common for big objects, but it's not unheard of either. And so it's possible to have some really big differences in sunlight depending on where you are from the sun. All right, everybody, that concludes today's episode on Kepler's first law and a quick look at ellipses. Thank you, everybody, for your attention. I'm Dr. Christopher Sorolla, speaking for Conceptual Astrophysics videos and Clear Skies.